Hi everyone, it's Loic at controlsnyc. Last video, I talked about my experience learning Niagara 4 and what I learned. This video, I'm going to talk about my research on the Chrysler Building and what my initial designs are going to look like. So, the Chrysler Building was built in 1930, and it was the first fully air-conditioned skyscraper in the world, which I thought was really cool. I unfortunately couldn't find any official information on the HVAC systems, since all the blueprints that are in public records are very outdated or just don't exist. I even called the place, but unfortunately I couldn't get a hold of anyone. However, I was able to find some floor plans, and a few unofficial sources mentioned one AHU per floor with the VAV box system, which I was able to tentatively confirm across a few different websites, and that's what I'm going to go off since that's the typical approach to skyscrapers and large buildings. I also tried finding the location of cooling towers by looking at the satellite view on Google Maps and Google Earth, and I believe there were a few on the roof near the gargoyles, but not big enough for the entire building. Then, I looked at an infrared image of the Chrysler Building, since these skyscrapers often have mechanical floors filled with HVAC equipment which has a higher heat signature. And sure enough, there's a high heat signature right here, around the 30th floor, and that tells me where all the outdoor units are. So I said we're going to do one floor first, so that means I need one AHU with the necessary points in VAV boxes. But what does all that mean? Colin covered AHUs extensively in Friday's video, so I'm not going to go too in depth about them here. Essentially, an AHU blows air across pipes filled with hot or cold refrigerant, in this case water, which heats or cools the air for it to be distributed in ductwork. They can control all aspects of air such as temperature, pressure, humidity, and purity. Next, we're going to be using VAV boxes to distribute the air. I think this diagram does a great job of explaining what a VAV is and does. A VAV stands for variable air volume, which means that it can control the amount of air going into a room with an adjustable damper while keeping the air temperature constant. This leads to a very efficient way of air distribution because each room can have its temperature controlled individually and the air doesn't need to be cooled or heated to different temperatures. It just needs to be kept at a constant temperature. So let's take a look at what the points are going to look like. Brief reminder, analog means it's a number, like a temperature, and binary means it's yes or no, 0, 1, true or false, one of two choices. Alarms are going to notify the system if and when something happens by routing to an alarm class and then an alarm recipient. So first, we're going to have the different control dampers, the supply, mix, and return damper, and these are all analog outputs because they're controlled by a motor, which dictates how much they turn. Then we have a bunch of temperature sensors, the supply, return, mixed, outside temperature sensor. These are all analog inputs. Then we have the supply, humidity sensor, and the return humidity sensor. These are also inputs because they measure the amount of relative humidity. Next, we have a humidifier and dehumidifier, which are controlled by analog inputs. Then we have a filter status, which is an analog input, but that's routed to an alarm, just to let us know if this filter needs to be changed. Next, we have the cold water valve and the hot water valve. These control how much water goes into the cooling tubes that the air is blown over to keep the temperature of the air constant. Next, we have the supply smoke detector and the return smoke detector. Again, these are binary inputs because they either detect smoke or they don't. So these are also going to be routed to alarms. Next, we have a supply air pressure sensor, return air pressure sensor, and a high static pressure switch. So these all measure air pressure or quality. The high static pressure switch is used to prevent fire from spreading, so that's why there's an alarm router to it. The supply fan VFD and the return fan VFD, these are actually the motors that control how fast the fan spins, so that's why they're analog outputs. Then we have the supply fan status and the return fan status, which are both Boolean binary inputs because they're either good or they're bad. We're also going to need a points list for the chiller, boiler, VAV boxes, and the cooling tower. So a lot of these are temperature sensors, VFDs for fans, pressure sensors, pumps, pump statuses. There's 2 pumps in the chiller because I'm going to use a lead lag runtime component to change them out, so I need at least 2 pumps. Next, the boiler, there's another VFD, a damper, some temperature sensors, pressure sensors. We have the VAV boxes, we just have a temperature sensor, a damper, and a reheat valve. That's for the coil inside the VAV box that's going to be heating the air. And the cooling tower, again, we just have a damper, pump status, fan status, VFDs, and temperature sensors. So pretty standard stuff. We have a couple of alarms linked to these. such as the statuses and the supply temperature sensors, just to make sure that they're not too high, or else that could damage the equipment. And that just about covers all the points that I'm going to be using. So I have the points list, which is a good part for my proposal. In the meantime, I'm going to start teaching myself about diagrams, but this is also a sequence of operations, which is a very important part of the proposal process. So a sequence of operations is a document that explains how the HVAC system is going to work and what everything is going to be doing. So for each piece of equipment, it explains one, general. So this is a basic description of what a component does. For example, a heating coil provides heating to the room. As simple as that. 2, system off. What happens when the system is closed off? For example, the valve is closed. Very easy. 3, blank control. So this could be humidity control, temperature control. Basically, it's describing what the equipment will be doing a little more in detail. So for example, it will explain how it will run once the system starts. So whether it's going to be running continuously or on intervals, the specific temperature or pressure or set point it will be sent to, and the allowable error. Next, there's alarms. This is a synopsis of the alarms that it's going to be connected to. For example, a heating coil is tied to a space temperature sensor, a supply air temperature sensor, and an airflow sensor. And if any of these pick up an anomaly, which is defined in the sequence of operations, then an alarm will go off. For example, if the temperature is more than 4 degrees above the set point for more than 10 minutes while the equipment is running, then an alarm will be sent to the BMS. 5 is a points list. We just reviewed a points list. Essentially, this just names the components associated with the equipment and what type of input or output it processes. This is also where it's indicated if a component such as a sensor will be available in histories, meaning if its activity will be logged and able to be reviewed. This entire process of sequences of operations has to be repeated for all components. And that just about wraps up today's video. Next video, I'll be starting my proposal with diagrams and a points list. If you have any questions or advice, please leave a comment down below. Consider subscribing to our channel, and thank you for watching. I'll see you soon.